right? And so today we're going to see one more concept about wellbore stability, and then we'll talk about the exams and the homework, okay? The homework solution. Let me increase the volume of this. Okay, so the last topic that we have to discuss is about strength anisotropy. But before we do that, let's go through a quick review about other factors that affect wellbore stability. So in addition to the ones that we saw about shear failure that produces breakouts and tensile failure that leads to drilling-induced fractures and sometimes to low circulation if that fracture goes beyond what is a small fracture, we have to consider also the effects of temperature. Basically, temperature is going to add tensile stresses that could lower your breakdown pressure. I was checking the exams, and I noticed that there was some inconsistency in the equations that I put in there about the signs, most of it, and some of you already noticed this. And I had a negative sign here, assuming that thermal stress you will compute it as positive. But let's just stick to what we have in the class notes. This should be a positive sign, and the thermal stress, if you have a negative change of temperature, should be negative. So this stress is going to be negative, and when you put something negative added to something, then that's going to subtract something, and it's going to make your PV smaller. So check in the exams there is a negative, but it should be a plus, okay? And I'll make sure that I correct this in the new equation sheet for the exam. But in summary, sometimes I do not, I didn't change that before, I didn't notice that before, because I don't try to memorize equations, and you shouldn't do that either. You should try to remember and to think about what the process is and what makes sense. And in this case, it makes sense that if you have a lower temperature, that's going to produce tensile stresses, and that's going to make your PV slower. So you should be subtracting something to the equation that you had before. Okay, so that was the first one, the effect of temperature. The second one is the effect of shearing stability. Did I record? Yes, I did. Okay. Okay. The second effect is the effect of shearing stability, and this is linked to the fact that clays are sensitive to the brine salinity. When the brine salinity is high, they tend to pack up more closely. When the salinity is lower, or when you freshen the water of the shale, the shale tends to expand, and that expansion can cause breakouts around the wellbore, because you have more compression around the wellbore, more compressive hoop stresses, and also your rock may get a little bit weaker as well. And we saw the solutions for that, something that you should remember, but I'm not going to mention again. And the third fact that you should take into account is the loss of mud support. And this is basically an effect that you may lose your effective radial stress support when you lose your mud cake. When you lose your mud cake, you lose this sharp gradient between the pressure in the wellbore and the pressure in the formation. And when you lose that, you have a reduced radial effective stress support. If you have a reduced radial stress support, notice that in your equations of, especially on PW shear, that's going to be very important, because on the equation of PW shear, your radial support is PW minus PP. If this quantity is smaller, that means that your sigma 3 is going to be smaller. And if your sigma 3 is smaller, let's do this in a plot. This is sigma 3, this is sigma 1, and we know that shear failure tells us that if we are somewhere over here, the strength of the rock is going to be this much, but if sigma 3 is smaller, the strength of the rock, or the sigma 1 peak that it can receive, is going to be smaller too. So reducing the effective structural support is going to make that wellbore less stable for shear. In some examples, if you were drilling an unconsolidated sand, if you lose that radial stress support, your wellbore may collapse when you get to that point, because you don't have any more radial stress to keep that wall in there stable. All right. So, and the last one that we're going to see is stress, especially strength anisotropy. And this one particularly applies to deviated wellbores. And probably you remember that we discussed a long time ago about the effects of strength anisotropy. If we have a sedimentary formation in which usually we have layers, we said that it's not the same to fail a rock which is drilled perpendicular to bedding or vertical, or to fail a rock which is horizontal, or to make or fail a rock which is at an angle, let's say in this case 45 degrees with respect to bedding. Either if you do a compression test or a tension test, is not going to be the same. And for the particular case of, let's say, a compression test in which we're going to fail the rocks in shear, what we usually see, not all the time, sometimes it can change, okay? It depends on how weak these planes are. But what you see most times is that the vertical rock is going to be the strongest. The horizontal rock is going to be stiffer but weaker than the vertical. Let me exaggerate that a little bit more to make the point. And that your rock at 45 degrees is going to be even weaker than the other two, because in this case of compression, and if we are talking about 45 degrees, those planes may line up with the direction in which you expect to have the highest amount of shear. All right, so this is a case for a compression, but you could do the same thing with tension, and you will see that there is also an anisotropy of strength for the tensile strength. It's not the same to load it or to pull it from here to there, like that, or to pull this one from here to here. And the response is going to be different. So I have some images to share with you that probably are going to illustrate this concept. a little bit more. And let's see if I find it quickly. Okay, so these are images of a shale that you can see the planes of lamination. This one is vertical to bedding, and it was failed in shear. You can see how fractures develop, and sometimes how the laminations, particularly in the previous case, how the laminations also like to concentrate fractures in those planes. Like that fracture, you see it's going through the lamination planes, and sometimes some of the fractures that are at the angle that you would expect, they deviate when they get to some of these laminations. So here this is another example of a vertical. This one was done at a higher confining stress. Here we have one more of a vertical. I like to go to the one of, this is an example of horizontal bedding. Now the sample is horizontal to bedding, and you can also see how now the bedding influences some of the fractures. We see, you remember that for shear we also always expect a fracture at an angle, but fairly steep. Well, in this case, okay, I just missed it. Okay, there. So in this case, you have some of those fractures which are inclined at an angle, but you also see some stray fractures that are now caused by those lamination planes. And the weaker those interfaces are, the more of these fractures you're going to see. So, you know, with these images, they help you to see actually how rocks fail, real rocks fail. It's not what sometimes we assume, but it's a lot more complex. This is another example of a sample loaded in a triaxial test parallel to bedding, and I want to catch this one. You see that we have a main fracture here, but when it gets to the bottom, it kind of branches on many other fractures that like to be more or less at an angle of what you expect for shear, but are very likely initiated by all these heterogeneities going from one type of rock to another type of rock to another type of rock. All of those laminations help the rock to break. And they also help to something that we're going to see later on, to create points of high stress concentration that favor propagation of some of those fractures. And the last ones, well, this one is still parallel to bedding, and again you see how you can see many fractures that they like to follow the lamination of the rock. And the last one that we're going to see are rocks now loaded at 45 degrees with respect to bedding. And we see kind of a main fracture, but then that it crosses some of those laminations, and that it goes like in staircase, crossing some of those layers, but then following what you expect for shear. And also notice in this example how the fracture, although it like to go straight like this, it doesn't do that. It goes through some of the lamination, then crosses, follows the lamination, crosses again, like in this case, and then follows the lamination. Why follows the lamination or the changes of rock type? Because those interfaces concentrate stresses, and sometimes they're also weaker than the layers themselves. And I think there are two more. Here you see the same thing, right? How the fracture crosses, but how many times it likes to go through the interfaces between the types of rocks. Like this one, like that one, same pattern as before. And I think there's one more. Anyone knows how Jeffrey got these images? This is a CT scan, right? It's based on X-ray technology. The same thing that you do when you break a bone. We do it for rocks, but we do it in 360 degrees to allow to reconstruct these tomographic images. And keep in mind, these are not real photos. These are it's a tomographic reconstruction. It's a digital image. Okay, so what happens when you put now this into a problem of wellbore stability, into drilling a wellbore through a laminated rock? Well, you get breakouts that are going to be probably different to what you would expect with a isotropic rock. So here you see, for example, a wellbore that if we assume that the lamination is horizontal, this one will be a horizontal wellbore, right? This is the lamination, and these are the breakouts, and you can see that some of those fractures sometimes they like to follow the lamination. And this one also will be a horizontal wellbore, and this one as well. Here is very clear how now the lamina are not exactly horizontal, and you can see how those influence the fractures around the wellbore. It gets a little bit more interesting when you have now that case, right? Now in this case, the stress, it comes in this direction, and it produces breakouts here, and you can see how these fractures extend out of the wellbore. Here the breakouts, and similar to what we saw before, some of these fractures they happen in several parts in here, like kind of like poker chips. You see that, like those how they accumulate in there. And same as before, sometimes they like to follow the lamination and continue out of the wellbore. But probably the most interesting case here is the one in which the wellbore and the stress does not coincide. So in this case, the stress is in this direction, lamination is in that direction, and you can see how first of all, the breakouts do not happen exactly where you would expect. Probably they start where you would expect. But notice how this breakout grows in this direction and this one in that direction. So they, because of the strength and anisotropy of the rock, is easier to form breakouts here than there. If the rock were to be isotropic, you will find them there. Actually, the maximum stress are here, but the combination of stress and strength of the rock makes the breakouts to be more likely to happen in this direction. And here you have a more dramatic wellbore breakout. So if you are analyzing a deviated wellbore that goes into a laminated rock, and most sedimentary rocks are laminated, some are more or less anisotropic, you have to take into account that, and you have to take into account what is the angle between what you expect is going to be the direction of loading with the direction of the lamination. And if you ignore this, sometimes you can make some serious mistakes, and your math window may be quite a bit off of what it really is. What you calculate may not be very accurate. And just to summarize what I was showing over here, what we were saying is that whenever you have a wellbore and you have stresses that do not coincide with the direction of the lamination, your wellbores may not be located here, but may locate in some other region that is not what you expect a priori. So when do you have to refine your calculations when you are working on wellbore stability? Well, there are some wellbores that are relatively cheap and in very well-known areas that you may not have to do a very refined geomechanical analysis, but you can go to offshore locations where a wellbore is $100 million, right? And where having wellbore stability or low circulation problem can be very, very serious. So in those cases, you really need to go into more detailed analysis. Probably some of the questions that we use may be limited, but you know in which direction to go in that case. You will have to consider strain anisotropy, and you will have to be a little bit more careful about your assumptions. All right, so with this, we finish all the conceptual part of wellbore stability. I remind you, if you're not doing things related to class, okay, just please do not distract the people in the room, the ones that are behind you, okay? So just be respectful to all the people in here. Some of you are paying attention to the class. If you are not, you'd rather check the videos later on YouTube. Okay, let's talk about the exams. So I propose the following. The homework is already uploaded. You can see the homework here. And Mohammed already posted all of those. And if I remember correctly, this exam includes everything from 6 to 9. So you have all the solutions there. They are very well explained. And for those that like coding and like Python, there is some source code that you can use in order to solve the homework or apply it to some other topics, but it's everything there. So what I propose that we do in this limited amount of time is that we go through the exams. If you have any questions, we discuss that. And if we have additional time, we come back and discuss the homework. Okay? All right. So let's go and talk about, you have a question? Yes. Can you repeat that? I didn't hear.
When you draw the stirring net and you draw the plane, you get to different angles. Which one do you use?
To different angles. In which specific case?
In all cases.
So you mean you get two solutions?
Two angles.
Well, you have to report those two.
But in the website that you gave us, only one works.
Say again?
When you draw them in that website you gave us, only one of the angles works.
I try to always give two. Probably you could tell me exactly where I gave one. I could help you with that. But for example, here I always give you two solutions. These are called the conjugate solutions, right? It's the same as looking for the square root of a parabola. You get two solutions. This is very similar. And here you have these two. By the way, guys, in the PDF notes, you still have the old figure. Some of you pointed out that there was something here that it wasn't making any sense. And there was an old figure that now I updated to the one that I used recently, in which the stereo net corresponds to what you see over here. In that old figure, the stereo net did not correspond to what you see over here, but corresponded to something else. So be careful with that, okay? But this is the correct one, and in the website you have the correct one right now. Wait a minute. I don't know if I answered your question with.
I was only for the notes
In the, you mean the handwritten class notes? Well, I'm pretty sure I gave two solutions, but then if you tell me exactly where, I can take a look at that. Okay. 1 minute. Yeah, you had a question.
Yeah. So on the bottom of this page,
yeah.
5.2. Can you scroll down to that? Can you explain how you get the first and second fault on the right side? We're trying to go over this in class.
All right. So these two.
Yeah.
All right. So how do you solve this problem? This is the problem of ideal orientation of fractures, hydraulic fracture and shear fractures or faults. You know what is the state of stress. So the first thing that you do is you draw that. Whenever some of your horizontal stresses does not line up with the north or the east, I would recommend that you make a top view plot, because drawing this in 3 dimensions is going to be extremely difficult, okay? At least for me. So just do a top view whenever your horizontal stress does not coincide with the north or the east. All right, so this is just from here. Up to now, everything okay?
Yeah.
All right. So the second thing is now to see where those shear fractures are going to go. In this case, this is strike-slip faulting, right? So if this is strike-slip faulting, that means that the shear fractures are going to be a combination of sigma 1 and sigma 3, both of them horizontal. And if you remember what we said about the x, that x is going to be here, and therefore those faults are going to have a dip of 0, a dip of, of 90, because they are vertical planes. And the only thing left is to calculate what is this angle, right? And that angle comes from the friction angle. The friction angle in this case is 40 degrees. So the angle beta is 65 degrees. So 65 degrees is going to be the angle from the plane of sigma 1 to the plane of the fracture. Either this one or that one is also 65 degrees. And because this one is 65, this one is going to be 25, and because this one is 25 and this one is 35, this angle must be 10. So this is the order in which you go. First beta, then you may need this other angle to relate it to the actual strike, and the last one is going to be 10. Yeah?
I guess the only thing that kind of confuses me on this is the labeling of fault 1 and fault 2.
Yeah.
When you originally go that 65 degrees, that's where it says fault 2. It doesn't matter which one's which, right? Because they're just conjugates.
It doesn't matter.
Okay.
It doesn't matter, because we could also have computed here 25, right? And if this one is 25, still that angle is going to be 10. Yes.
So off of that though, based on, you always go parallel to SH max or S3, correct? And then you go the angles from there. Like when you're initially drawing the strike line, like just that dotted line that goes
Yeah.
from the top to the bottom.
Yeah.
That's where we start, and it's always going to be parallel with SH max.
This line,
Yes.
yeah, this is the direction of SH max.
Okay.
It's always important to remember that these faults are going to be at equal angles from the direction of sigma 1, right? For example, when you see this case over here, this is the direction of SV in the middle of the two faults. This is the direction of sigma 1 in this case, and in this case, this is the direction of sigma 1.
And is S1, S2, S3 always going to be the smallest, the middle number, and the largest?
Yes,
Okay.
correct. Yep. Yes.
So when we're trying to find these strike orientations, the best way to do it is just pretty much turn it into a geometry proof. If it's rotated from the north, and you're trying to get that angle,
What do you mean with geometry proof?
like you're just like solving right triangles or.
Yeah, this is just geometry. The part of geomechanics is here to recognize where those planes would be. After you do that, it's just determining angles, which is just geometry, trigonometry. Yeah.
I guess it's pretty difficult to indicate because this is in 3D, but how would you indicate like the friction angle of that? Like where would you place the friction angle?
Here?
Yeah.
What do you mean? How would I put the friction angle? So the
So if you
orientation of the fracture is already a consequence of the friction angle. Does that make sense or no?
No, because I thought
Okay.
like, the friction angle. So if you go back up to the 3D zone,
Yeah.
we could, yeah, that one. Maybe it's not. Maybe
Oh,
it's
don't be confused. This is not a friction angle. Okay? This is not a friction angle. This is just the strike. It happens to be 30.
Right.
But if that's just because the friction angle in this case is 30, and that makes that one to be 30, but if this one was to be, let's say, 20, then this one will be 45 plus 10, 65. This one will be 25.
So you can indicate the friction angle.
No. Here there is no friction angle in here, but these angles they depend on the friction angle. But there is no friction angle in those. Yeah.
So, is the dip for both of them, are they both going to be 90 degrees?
Yes.
Okay, so like every single time, like we can look at what type of fault it is, and
Yeah.
then automatically know what kind of dip is based on that fault. For
As long as the vertical stress is the principal stress, what you say is correct. Always in strike slip, you already know the solution is going to be the dip is going to be 90. Okay?
If it's rotated, it'll change.
Yes.
Okay.
Always in normal faulting, you know that the dip is going to be the angle beta. Friction angle divided by 2 plus 45 degrees. Always in reverse faulting, you know that the dip is going to be 90 degrees minus the angle beta. But the other things are still, the other angles still, you have to determine those. Yeah.
I think you remind you to talk about the conventions for drawing faults on the 2D fault, like the signs.
Oh, yeah, these ones. So we didn't talk much about these geological conventions, right? But let me explain what this means. This one means that we have here, this is a vertical plane. It's a cross. This one means that it's a plane at a dip. It's dipping at a certain angle, and that's the line of strike. Let me zoom out a little bit more. This is the line of strike and this one is the direction in which the fault dips. Okay, line strike, this is the direction with the fault dips. Don't be confused with the stereo net projection in which, for example, this plane will be like this, and in stereo net we plot the pole going this direction. But it's not the same. This one is just a geological convention which tells you that deep is in that direction. Yeah.
Can you go back up to the 3D?
This one?
Easier. So I don't know how to draw the dotted line on
The dot, this one?
Yeah, like the, yeah.
So all these dotted lines represent planes. Okay? Which planes? The shear planes. And all of these follow this. I think it's in the previous one. Wait a minute. It seems I don't have it in there, but I have it here. All of them follow this principle, in which we know that based on shear failure, a fracture will be ideally oriented at an angle beta from the plane of sigma 1 towards the plane of sigma 3, where beta is 45 degrees plus friction angle divided by 2. Those are the solutions of that, either in one direction or in the other direction. Those are the two possible solutions. Those are those dashed lines that you see over there. Yeah.
So when we're doing these 3D drawings, is it safe to say that I guess the X of the two faults crossing, would that be on the face perpendicular to sigma 2? Yes.
The X.
Yeah, just where they cross, where the primary. and
Well,
secondary-
I would say more like imagine like these two planes, right? Like an X. The line of the intersection of those two planes is going to be a line. That's the direction of sigma 2.
Okay.
Always. All right, guys. I can continue answering questions or go through the exam. Let's make a poll now. What do you want? Exam? Exam? Okay. Questions? More questions? Specific questions?
Right. Can we go
Uh,
through the most costly questions in the exam?
Okay. Again. Okay. Raise your hand for exams. Let's go through exams. Okay. Questions? Specific questions? Okay. Well, we'll go through exams because the majority wants that. Okay. But, feel free to stop me here. There is something you don't understand or you have a question about, right? Okay. So, conceptual part. Same as always, okay? Do you have any specific question about this conceptual part in this one? No? Okay. We'll go here. Again, I recommend you to read the book notes. Everything is in there, and everything I do in here, it belongs to there. And I do not cover things that I didn't talk about in class. So there may be things in the book that I didn't cover here in lecture. I'm not gonna talk about those. Okay, this is a very similar problem to what you did in the homework, right? You have a top view. You can see the trajectories of horizontal wellbores, and you need to justify why the operators here went in that direction. And why? Because this is the minimum principal stress, right? And if you do that, you obtain fractures perpendicular to the minimum principal stress. Remember, the fractures are planes, okay? They are not lines. This is a simplification. And a hydraulic fracture plane is going to be perpendicular to the direction of the minimum principal stress. All right. based on this, second thing I ask you is, if you know what is state of stress, I want you to tell me what kind of faults you would expect in that location. So here I use different type of keywords to say the same, like what kind of faults may have been created, or what kind of faults would you expect, or what would be the ideal orientation of faults that would happen in this place. These are all the same, okay? All the same thing. It means that what is what you would expect, what would be the ideal orientation of faults. And in order to solve this problem, you have to do what we were talking just 10 minutes ago. You need to recognize what is the maximum principal stress, which in this particular case, I'm telling you that this is normal. So if this is normal, what is the maximum principal stress? Is vertical. So this is like this. It's a vertical stress, and the X or the faults are going to be like this. The strike is going to be perpendicular to SH mean, or in the direction of SH max, and the angle of these faults, the dip, is going to depend on the angle beta. I don't like to enforce rules, okay? But if that makes your life easier, you may want to go ahead and remember that. In normal faulting, the dip is going to be directly the angle beta. 60 degrees, that's what you see. 60 degrees, either dip into the northwest, which is this one, or to the southeast, which is that one.
So are the dips interchangeable or not?
The what?
In this solution, are the dips interchangeable? Like if you put 60 degrees northwest for that, is that accurate?
Yeah, that's one of the solutions. So either could be F1 or F2.
Okay.
Yes.
It doesn't have to go with the strike.
No. Well, the strike is the same, right?
Right.
For those two, is the same. Okay. And then I'm asking you also for, no, I'm not asking for a hydraulic fracture. I'm just asking to put that in a stereo net. And the stereo net will tell you that if this is something like this, 60 degrees, that point, that pole is going to touch the lower hemisphere right in there. Still, it's not late, guys, to stop by my office, say hello. I don't have candy like Errata, okay? But actually, I do have some chocolate-covered almonds from Folger, Louis Folger, that he, they always provide. They always provide this candy to the department. They are fantastic. So I'll give you some if you stop by. So right after class today. So if you stop by, I'll give you these cards, and you can make these on your own. But I'm going to allow you to have these to help you. Okay? If this helps you, you can have it in the midterm. Okay. Any question about this problem? Yeah.
So wherever the pole touches the bottom of the sphere,
Yeah, bottom of the sphere. Yeah. That's where the dot goes. Remember, check this online app that allows you to plot that in 3 dimensions. That's very, very easy to look at and to understand. Okay, so we're running out of time. So let me just continue to go to a wellbore stability problem, and then we can come back if we have time. Second problem in this exam, it's a problem of, again, when I mean frictional equilibrium, I also mean limit equilibrium, or I also mean equilibrium of faults, or this is also the same to say as the state of stress is limited by the strength of faults. It's all the same thing, okay? So, in this problem, what you have to do is you have to calculate opposite, well, you did also dynamic homework, but usually we calculate the minimum principal stress. In this case, you know what is the overburden, you know what is the pore pressure that allows you to calculate the vertical effective stress based on friction equilibrium of faults or limit equilibrium of faults. You can tell what is sigma 1 because you know sigma 3. This is reverse faulting, so it's SV sigma 3. Sigma 1 is going to be sigma H max. You add pore pressure to that and you get the value of the maximum total stress. Yes?
So in the homework, I noticed that the PW shear wasn't really used. Like we didn't really use PW shear to determine the mud window.
Yeah, correct.
Is that a common trend, or so? If you ask us to make a mud window, do we not bother?
Well, the PW shear, usually you may want to go a little bit lower than PW shear, right? But there might be some applications in which you do not want any wellbore breakouts at all, because probably there is a region in which you have zonal isolation problems and your cement doesn't go well into breakouts. You may say no breakouts, okay? But it's also, I presented this value of PW shear as an introduction, as a first step to go further and calculate the PWBO for a given breakout angle. Any questions about this problem?
I have a question about this problem.
About this problem?
Kind of.
Okay.
In the notes, it said that if you go below PW shear, then you have a breakout in the wellbore.
Yeah.
So you're saying the mud window should be below PW shear, or
It can be below PW shear because sometimes you can have breakouts, but the wellbore will not collapse. Will be still stable. All right. Yeah.
Is that statement true that sigma H max equals Q sigma B? Is that just frictional equilibrium? Like, was it given in the problem?
Sigma H max equal to sigma V. This is only for reverse faulting. Okay? This changes. So this is always true, but which is sigma 1 and sigma 3, it changes according to the local stress regime. All right, and let's go to the next one, which is a wellbore stability problem. And notice that here I'm already asking you for a horizontal wellbore, okay? So you need to know how to use the equations of a vertical wellbore for a horizontal wellbore, okay? The only thing that you have to do is you have to change these two for the appropriate values that correspond to the horizontal wellbore. And in this example, I'm not asking you to calculate PW shear. I go straight and say we want a mud window with a breakout angle of 60, and this is what the equation tells you. These are now the appropriate stresses that should go into the equation, sigma V and sigma H max, because this is a wellbore drilled in the direction of SH mean. And in this case, here in the problem statement, I'm saying that these are natural fractures in this wellbore. And if they're natural fractures, very likely at a large scale, the tensile strength of the rock is going to be 0. If the tensile strength of the rock is 0, that means that you cannot account with that in the calculation of pressure breakdown. This is like the example of that piece of rock that I showed you. You remember that I asked you if I could pull it with my hands. And you told me no, but I rotated it and I did. That's because there was a fracture in it. If you have fractures, the fractures may not be cemented, and that may not give you any tensile strength at all. So I'm going to stay a little bit longer if you want, okay? So if you want to leave now, just be welcome to leave. If you're going to stay longer, I can stay longer to answer some questions. Okay, let's just give like 2 minutes to everyone to leave if they want to leave, and we'll continue.
I just have a question. So for the link you gave us for the chapter 5 and 6 notes for on Canvas,
Yeah.
is that any different from the get to the textbook?
Well, the PDF is a version that it was the most recent version up to last week.
Okay, so
But this one, I updated it today.
Okay, so I'll use this one.
And it has a few more things to do. Okay?
Thing there, so in this like problem, you gave us those angles on this. And when I did